The James Webb Telescope pointed at what astronomers thought was one ancient galaxy, and instead found 6 smashing into each other 12 billion years ago. This isn't just a demolition derby in the early universe. It's a fossil record of how the galaxy you live in got built, 12 billion years after the fact. The discovery gives scientists a rare, direct look at how the largest structures in the cosmos and the black holes at their centers grew up together. What they found changes the story of this specific patch of sky and sharpens our picture of how the universe got organized. These 6 galaxies are caught red-handed, becoming a single monster. The kind of galaxy that normally takes billions of years to notice, let alone catch mid-assembly. Astronomers call the object itself a protocluster, the blueprint phase where matter started clumping together just 1.8 billion years after the Big Bang. These 6 galaxies, collectively named TGSSJ 1530-49, aren't lightweights. 4 are already massive, and together they are on a collision course to form a single, brightest cluster galaxy, the most enormous type known. But the most stunning part is their density. This system packs hundreds of billions of stars into a region smaller than our own Milky Way. The 6 galaxies span a volume only a few tens of thousands of light-years across, making this one of the densest collections of heavyweight galaxies ever found in the early universe. This incredible density of gas and stars is fueling an absolutely frenetic pace of star formation. And that pace reveals just how different this environment is from our quiet galactic neighborhood. The Protocluster is churning out new stars at a rate of somewhere between 70 and 163 solar masses per year. For comparison, our Milky Way produces fewer than 10 solar masses per year. This isn't a factory running a faster shift, it's 16 Milky Ways worth of star birth happening in one place at once, driven by the gravitational chaos of the merger. All of this churning gas and dust does more than just build stars, it also feeds the monster at the center of the storm, which JWST's infrared eyes couldn't see on their own. At the heart of this maelstrom is a supermassive black hole, and finding it required a completely different kind of telescope. The tip-off came from radio astronomers who saw emissions typical of an active black hole. Scientists call it an ADS-RG. And here's the weird part. Normally, a black hole's glow is so bright it drowns out its own galaxy, but ADS-RGs offer observers a better look at a galaxy's stars, gas, and dust because their radio emissions come from jets of plasma rather than from an active galactic nucleus, AGN. But in a high redshift radio galaxy, the dominant signal comes from jets of relativistic plasma shot out from the black hole's poles, which emit synchrotron radiation at radio wavelengths. This lets scientists study the black hole's activity and the galaxy's stars at the same time. And the radio image they got was incredibly sharp. A team led by Christina Gabagni used a network of connected radio telescopes across Europe to get a high-resolution image of the black hole's activity. This implies the black hole is still young, its jets not yet powerful enough to break out of the dense gas of their host galaxy. This two-pronged approach, infrared from Webb, radio from the ground, is how we now know the black hole is right inside one of the 6 merging galaxies, confirming our theories about how these violent mergers fuel black hole growth. But the most important number JWST delivered wasn't about size or speed, it was a correction. The James Webb Telescope's new, far more precise spectroscopic data unambiguously placed the system at a redshift of 4.0. It's a perfect example of how science self-corrects and how better tools give us a sharper, truer picture of the universe, even when it means a celebrated record gets erased. And what this truer picture shows is a startling match for our best theories. Researchers noted that this real-life protocluster qualitatively resembles what cosmological simulations predict for how the universe's biggest galaxies form. Our models have long suggested that these giants assemble through a rapid succession of mergers in the early cosmos. Finding a system in the wild that looks just like the simulations gives scientists confidence that their models of how the universe organized itself are capturing something real. Based on their speeds and distances, the 6 galaxies are expected to fully merge within a few billion years. But that just raises the next big question. This discovery provides a rare snapshot of cosmic construction, but the work is far from over. We can now watch the buildup of a giant galaxy and the growth of its black hole in tandem. The key question is whether those young, compact radio jets will eventually break free and grow into the massive structures we see in the modern universe. or if they'll remain confined by the sheer density of their violent birthplace. This is how we learn how the universe's largest galaxies took shape, by finding one in the act and using every tool we have to see the whole picture. Stay patched.